In the next section of the lecture, I will talk a little bit more about electrofluidic effects. And these are effects where electrical fields are used to either handle fluids or to handle particles in fluids. And there are quite a number of those effects actually. And in your PDF slides that you can download, you find this slide where I outline some of the most important ones and with a short explanation of what they actually do. In this lecture, I'm going to talk mainly about electrical double layers, electroosmotic flow, and dielectrophoresis, and a bit later in the course we're going to talk also about electrowetting. And if you want to know more in detail about these phenomena, you can always go into Wikipedia and read a little bit more about them. So the first effect that we're going to talk about is the electrical double layer. And what is an electrical double layer? Well, if I bring a liquid or a fluid liquid in contact with a solid, so I have a solid wall, and I bring a liquid in contact with that, what will happen is that I will create a chemical interface between, this is of course the solid, it doesn't have to be solid, but typically it's a solid, and a liquid. You see, if these are incompressible, if these are unmixable liquids, this could also be a liquid-liquid interface, but then things are a little bit more complex. So very typically it will be a solid and a liquid, such as the wall of a microfluidic channel and a liquid in a microfluidic channel. So I bring a liquid in contact with a solid, I create an interface where I have the liquid is always some sort of a solvent. If it's water or alcohol or oil, it doesn't matter. Liquids function as some kind of a solvent for chemical groups that are at the surface. And sometimes it's a very bad solvent, almost nothing dissolves, but there's always some kind of dissolving. So what happens is that some of the molecules that are at the wall or in the liquid will start interacting. Either I get absorption of charge groups on the surface, or I get dissociation from solid groups into the liquid. And so I get a partial, some of the molecules in the solid will, for example, split into ionic species, and then I get, for example, a positive charge that moves away, that is diffusing away from this, can diffuse away from the surface, and I have a negative charge that remains behind just at the surface in the solid. And so if I do that, of course, it takes electrical energy to do that. But on the other hand, it also decreases. So doing that requires electrical energy, but on the other hand, it also increases the entropy of the system. So if I have all my molecules neatly aligned still at the surface, that's a low entropy system. So the system wants to increase its entropy by some dissociation. So there's this balance between electrical field and the chemical dissociation that will always occur. Yeah? And so what does this mean now? Basically, I end up with a layer with some kind of charge in the layer, and here I give per example that I have a negative charge left on the solid wall. That is not necessarily true. Could also be a positive. That depends on the pH of the liquid and on the salt concentration and on the type of wall. So, but in this case, for an example, I'm just going to take that I have a negative surface charge that I create on the liquid. That I create on the wall, on the surface of the wall, a negative charge. So what's going to happen in the liquid? In the liquid, I will always have positive and negative ions, and they will typically be in equilibrium. For example, water dissociates. There's a certain portion of water that dissociates in a hydrogen, in an H+, a proton, and in an OH- group. Yeah, and you know exactly how much of the water dissociates in a positive and a negative group. You should know that by heart. It is exactly 1 out of 10 to the 7th molecules do that, 1 on 10 million. And how can you know that by heart? Because the pH of water, neutral water, is 7. That means that there is a 10 to the power minus 7 concentration of H+, and therefore also 10 to the minus 7 concentration of OH-. So I have some dissociation. But what happens now is that if I have negative charges on my wall, then my positive charges see that and they start traveling towards the wall. So basically what I get here is that I get positive charges like this negative charge. So there will be an excess of positive charges. There will still be here and there a negative charge also, but really there's an excess of positive charges close to the wall because they like these negative charges. And so I will get a buildup of a layer here close to the wall, a region close to the wall where I have an excess of positive charges. And if you do the physics behind that, you will see basically that I get a potential field that stretches out here, a potential field. I call that phi. And that potential field looks something like this. It's going to be looking like an exponential. And it's not going to zero, it's an exponential typically. But it has typically some exponential decay. And this is what I call the electrostatic double layer. It is a layer close to the interface where I have a net positive charge. Could also be net negative charge if I would have positive surface charges. So this is what we call here the electrical double layer. And the liquid out here, I call that the bulk liquid.